Hi, Mr. Sapone here, and today we're going to take a look at light in the electromagnetic spectrum. Visible light, the light that we see, is only a small part of all the light that there actually is. Light is a form of electromagnetic radiation, and a simple little experiment you could do is with a remote at home and a smartphone. Usually there's a light or some sort on the front of a remote. When you press the buttons, you can't see any blinking or any light being given off. But if you were to point that at a smartphone with the camera on in selfie mode and press it, you should see some light glowing. And that's because remotes work in a wavelength of light that we can't see, but your phone camera does pick up infrared radiation. These work in the infrared portion of the spectrum, but it's a quick little experiment you can do. The idea is that the light that we see, though, is just a small portion of all the light that there actually is. This is the full electromagnetic spectrum. When I was in college, I came up with an acronym to remember all the different types of wavelengths. God xylophone usually vibrates in many rooms. God gamma X-ray xylophone usually vibrates, which is visible light, and infrared many rooms. Radar radio waves. Gamma rays, these are really high energy, short wavelengths. Frequency is very high. So these are super energetic. These are the waves that I guess superheroes, it's how they get their powers. They're exposed to gamma radiation and then they turn into the Incredible Hulk or something. But these are very harmful if you were exposed to a lot of gamma radiation. If you're outside of, like, say, a protective spacesuit or outside of the Earth's magnetic field or anything protecting you or shielding you from this radiation, would not be very good for you. X-rays, we know X-rays because we get X-rays done. X-rays have the great property that they can pass through, say, skin and flesh very well, but they don't pass through bone so easily. So if you pass a screen of X-rays through a person, they're going to stop where they come into contact with bone, and that allows us to obtain an image of our skeletal structure. We can look for fractures or breakages and things of that nature. So those have been very useful in the medical field. And of course, there's ultraviolet light, which UV rays, these are how we get our tanning done, or cancer can be harmful as well. I believe bees actually use the ultraviolet. They see in the ultraviolet to do some things, but these are also what your typical black lights. Black lights are ultraviolet emitters. And then, of course, we have this small part of the whole spectrum right here, which is visible light. And it's a very small portion of the entire spectrum of light. This is the light that we can see with our eyes. We can't see any of this light over here or over here with our eyes. But it is all light nonetheless. The size of light, the size of the wavelength determines the type. So our eyes are good at seeing light from 380 nanometers to 700 nanometers. But we can't see any of this other light just because we can't. Our eyes did not evolve that way. Like I said, bees use the ultraviolet. There are some animals with sort of like night vision, or they see in the infrared. And you remember the colors of the rainbow using Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet. Red, orange, yellow, green, blue, indigo, violet. So again, red light about 700 nanometers, lower energy towards the blue-violet side, higher energy. Then, of course, we go on the infrared, our kind of night vision goggles, things of that nature. Microwaves. Microwaves are cool. This size of a microwave, that's how a microwave works at home. The size of this wavelength in a microwave is just the right size that it likes to vibrate water molecules. Water molecules have a specific size, H2O, and it turns out that microwave radiation really agitates them, makes them move, spin, do all sorts of things. So microwaves actually cook by vibrating or moving water molecules in things, or things that are similarly sized to water molecules. So just a little FYI. And then, of course, radar and radio waves. But the main point is that there's a whole bunch of light that we cannot see, and this is the total spectrum of light. So how does light form? We're going to look at one way in which light forms. And remember our 2882 rule. We have over here, we have an atom. This is the nucleus, protons and neutrons going in. And we have electrons and energy levels around the atom. Electrons don't orbit like planets, but we like to draw energy levels in terms of rings. This is energy level 1, energy level 2, 3, 4, and so on. So if energy, we'll say electrical energy, like say electricity, strikes an atom, one of these electrons, which was originally in its ground state, its original state, it hopped up a level because it became excited. When energy, electricity hits an atom, it becomes excited. Some of these electrons are going to jump up to different energy levels. Those electrons are not very stable at those higher energy levels. So what they're going to do is they're going to drop back down. So electrons are jumping up and jumping back down. And as they drop back down, they're going to re-emit that energy. And they actually emit a photon of light. A photon is a small packet, or the smallest packet or quantity of light possible. They're going to emit photons of light. Sometimes that light is visible. Sometimes we can see it. Sometimes we can't. But electrons jump up and they drop back down. And again, it's not just one electron doing it. And it's not just one energy level. This thing could jump up to energy level 7, drop back down to 5. Other electrons are going to be jumping up and down simultaneously. And it's going to be giving off a whole array of different types of light. Some of which we may be able to see as visible light. But that's how atomic theory, how we get light. Excited electrons jumping up to a higher energy level. As they drop back down, they're re-emitting the energy. Often enough, it's in a form of light that we can see with our eyes. So applying this, we're going to look at two types of light bulbs, incandescent and fluorescent light bulbs. Incandescent light bulbs work a little bit differently. They're thermal radiation. Everything above absolute zero glows. Kinetic theory of matter says all matter is made up of tiny little particles. Those particles are always moving. When we have molecular collisions, when little particles are colliding together and the natural state of affairs, they're releasing energy. So we're constantly emitting electromagnetic radiation. We're constantly giving off light. Everything above 0 degrees Kelvin, everything with temperature is giving off radiation right now. Just so happens that we can't see the majority of the radiation that we are giving off because it's in a wavelength of light our eyes can't perceive. Well, everything is glowing right now. And the higher the temperature, the hotter it glows. We know if you put a piece of steel, an iron rod, or a steel rod in a fire, eventually it'll start glowing bright red, or a stove burner eventually gets bright red. So the amount of radiation given off is a function of temperature. Higher temperature, more light given off. Or actually, we say more light in the visible sense. But thermal radiation is real. Everything is always glowing. And this is how an incandescent light bulb works. There's a tungsten filament inside. Tungsten's a metal, just a little metal coil inside. And when it's electrocuted, electricity runs through it. It just gets really, really, really hot. Those particles are smashing together. They're giving off visible light. And it turns out that these light bulbs are very inefficient. 95% of the energy is lost. Most of the energy, not lost, but it's given off as heat instead of light. That's why these bulbs get very, very hot in your room. And then we have fluorescent light bulbs. These are going to work using excited electrons. Electricity, what we have here is we have a glass tube. And, obviously we need electricity to make these work, but there's mercury gas inside. There's mercury vapor in there. And the environmental effects of that have been questioned by some people. As these things continue to break, we're continually releasing mercury gas into the environment. But that notwithstanding, this mercury gas is excited by electricity. So what happens is the electrons are going to jump up to a higher energy level. Electrons are jumping up, but they're going to return back down to their ground state. And when they do that, they're giving off ultraviolet radiation, or same type of light in a black light. Now, we can't see that radiation, so what good is a fluorescent light bulb if it's emitting radiation we can't see? Well, the outer portion of the tube is coated with a phosphor powder. And what happens is the UV rays are going to excite the electrons in the phosphor. And those excited electrons, they're jumping up and they're also dropping back down. And it just so happens that they're going to emit photons in the visible portion of the spectrum. So that's two different types of light, thermal radiation versus excited electrons. Pretty cool process. And last thing I want to talk about is emission spectra. We know that if we pass white light through a prism, we get a continuous spectrum of all colors. So if you ever pass white light through a prism or looked at a CD, which has a diffraction grating on it, you can see a full spectrum of colors. If you were to take a tube of hydrogen gas and you were to subject it to electricity, And you were to look at it through a diffraction grating, or say pass it through a prism for simplicity, you would not see a continuous spectrum. You would get a line spectrum. You would only see 4 lines. And it turns out that for other elements, each element has a unique set of spectral lines it gives off. This is, say, white light from the sun, or a white incandescent light bulb. Hydrogen right there. Then, of course, helium, argon, and so on. Each element's giving off a unique spectrum of light. And this becomes very important because it allows us to identify gases and things of that nature. In fact, that's how a lot of astronomy is done, because we can't actually get to stars to, put our hands. You can't grab a pile of star plasma and bring it back to Earth and examine it. The sun is 93 million miles away, and it's the closest star. So we have to actually study stars in space from a distance by analyzing light. So why does each element have a unique set of spectral lines? Well, and before we get into that, I just want to point out helium was discovered on the sun using this whole spectroscopic technique before it was ever discovered on Earth. And the sun is actually 93 million miles away. So we discovered an element on the sun 93 million miles away, not ever going to the sun, but just by observing the light. And that's how helium was discovered. Well, this is a hydrogen atom, and each one of these semicircles here is an energy level. It turns out that when an electron drops down from energy level 3 to energy level 2 in a hydrogen atom, it produces red light. When we drop from 4 to 2, green light, 5 to 2, blue, 6 to 2, purple. So each energy level, and there'll be a different one if it went from energy level 3 to 1, or say 6 to 1. There's going to be a whole host of different types of light that can be created depending on what energy level the electron starts at and what energy level it ends up at. And each atom has its own unique set of electrons, a different number of electrons, and a different number of protons. So they're all going to have a different sort of energy setup. So each atom is going to end up producing its own different unique set of spectral lines, because the electron configuration is different and the energy of the atom is different. There's different numbers of protons and neutrons and so on. And one final thing to look at, and this is how different types of wavelengths, this again is for hydrogen. Anytime you have anything dropping to the first energy level in a hydrogen atom, it go from energy level 5 to 1, 4 to 1, 3 to 1, or 2 to 1. You get UV rays, ultraviolet radiation. Visible light happens when anything drops down to the second level, and then of course infrared radiation up here. So this kind of gives us an idea of where these line spectrums come from, and to realize that as electrons drop down from one energy level to another one, they're going to emit a specific sort of energy, a wavelength that could be small, a wavelength that could be big, and it's really the size of that wavelength, the amount of energy emitted, that determines the type of light that comes out. So hopefully this helps you understand light a little bit better. This is Mr. Zapone.